part 5. In part 4, I discussed Raoult's law, applicable for volatile solutes, where we had liquid and liquid solutions. So, when Raoult's law is applied, we have a liquid A, we have another liquid B, where A is the solute, B is the solvent. So Raoult's law is applied to A, then it was PA is equal to P naught A into XA. When applied to component B, it is PB is equal to P naught B into XB. Now what is PA? What is P naught A? PA is the partial pressure of the component A in the solution. That is when A and B are together in the solution. What is P naught A? When the partial pressure of component A when it is not in combination of B, that is pure form. So we applied Raoult's law, and relationship we derived as total pressure P is equal to P naught B minus P naught A whole into XB plus P naught A. And we got a graph like this. This is P naught A, this is P naught B. This side XA is equal to 1, so XA is equal to 0, XB is equal to 0, XB is equal to 1. This is the total pressure. It is PA and this is PB. So this is the graph according to Raoult's law for ideal solutions. And we also discussed that for ideal solutions, mandatory condition is it should obey Raoult's law. Delta V mixing is equal to 0 and delta H mixing is also is equal to 0. That means there is no change in volume, there is no change in enthalpy. Before mixing and after mixing, the volume and the total volume and the enthalpy remains the same. Now we'll discuss non-ideal solutions. We categorized miscible liquids into 3 forms. Actually 2 forms, ideal and non-ideal solutions. Then non-ideal solutions is again of your 2 types. So for non-ideal solutions, or which solutions are called as non-ideal solutions? The solutions which do not obey Raoult's law at all concentrations. Do not obey Raoult's law at all concentrations. Then delta V mixing is not equal to 0. It may be greater than 0, it may be less than 0. Accordingly, 2 types of non-ideal solutions. And also delta H mixing is not equal to 0. Accordingly, delta H greater than 0 and then delta H less than 0. Accordingly, 2 categories of non-ideal solutions. So, when we discuss about ideal solutions and non-ideal solutions, we have to explain the interactions between the components A and B. So A component is there, B component is there, and after mixing we get solution or a mixture of A and B. So for A we have AA interactions, for B we have BB interactions, and for solutions we have AB interactions. When AB interactions are same as that of AA interactions and BB interactions, that category gives you ideal solution. Now, if the interactions are not equal, this is equal, here it is not equal, then we go for non-ideal solutions. So, first category of non-ideal solutions. First category of non-ideal solutions is your positive deviation. Now, non-ideal solutions are of two types. One is positive deviation, other one is solutions which show negative deviation from Raoult's law. Now, under positive deviation, suppose A component is added to B component and the partial pressure of component A is found to be more than that expected on the basis of Raoult's law. Similar effect is observed when component B is added to A. The partial pressure of B is more than that of A. Again, I am repeating. When A is added to B, if it is found that the partial pressure of A is more than that of B. If B is added to A, the partial pressure of B is more than that of A. Okay. Now, it is found that the total pressure, vapor pressure for any solution is greater than the corresponding ideal solution for the same composition. For ideal solution, I'll explain in terms of a graph. So, this side we took P naught A and this side it is P naught B. So, this is the vapor pressure, this is the total pressure. So, PA is equal to P naught A, P is equal to P naught A plus P naught B. This is PA, this is PP. So, this is the pressure of the solution. This dotted line is the pressure, partial pressure of A. This is the partial pressure of B in the solution. Now, if it is more than this vapor pressure for the solution, then it is called as positive deviation. So, how will we get the graph? It is like this. This means that the vapor pressure or the partial pressure is more than that it is expected according to Raoult's law. So, this is the total pressure. According to Raoult's law, we should have this pressure. But because it is a non-ideal solution, it is not obeying Raoult's law. It is having extra or more vapor pressure and then it is called as positive deviation. So, this is P naught A, this is P naught B and here this is total pressure. Now, when you talk about a single component, the vapor pressure according to Raoult's law should be this. But because A is added to B, it is found that it is slightly increased. Then that is it is expected according to Raoult's law. Now here also it is for B component, when it is mixed to or when it is added to A, it is slightly increased. Now when you have bulged out graphs, it is called as positive deviation. That is the expected, the vapor pressure for the mixture or for the individual components are more than it is expected according to Raoult's law. When this kind of graph or this kind of solutions are obtained, whenever we have AB interactions lower than that of AA interactions or BB interactions. For ideal solutions, it was equal. When it is less than, then it is positive deviation. Same thing, when you talk about positive deviation, delta V mixing is greater than 0. There is slight increase in the volume. Delta H mixing is also greater than 0. That is, greater than 0 means it is endothermic. That is, absorption of heat takes place. Now the example for this kind of solution is ethanol and cyclohexane. Other examples can be given like this: acetone, carbon disulfide. You can also give the example of methanol, water, ethanol, water. For remembrance purpose, we can give the examples of alcohol plus water system under positive deviation. Now, the negative deviation. The second category of non-ideal solution is your negative deviation. So, as we discussed, in case of positive deviation, the vapor pressure is increasing, or it is more than that, it is expected. Here it is less than that. So we have little depressed graph as we made for Raoult's law. It is depressed graph. Same way, this side will be taking P naught A, this side will be taking P naught B. So we can say the AB interactions are stronger than that of AA interactions or BB interactions. Again, one more thing, as said earlier, delta V mixing is less than 0. Delta H mixing is also less than 0. That means it is exothermic in nature. Now the example for the solutions showing negative deviation, it is acid plus water system. You can take the combination of hydrochloric acid and water, and then you can also take nitric acid and water. You can also take acetone and aniline. Now I'll sum it as we'll revise. When two components are added, perfectly we get completely miscible liquids, partially miscible, and then non-miscible liquids. Now for miscible liquids, we have two categories: ideal solutions and non-ideal solutions. Now these non-ideal solutions are again divided into two categories. One is positive deviation and the second category is negative deviation. For ideal solutions, the solutions, if obey Raoult's law, delta V mixing is equal to 0, delta H mixing is equal to 0. For non-ideal solutions, obviously they do not obey Raoult's law. Delta V mixing is not equal to 0. If it is greater than 0, then it is positive deviation. If it is less than 0, it is negative deviation. Then delta H mixing is not equal to 0. So delta H mixing, you can write in exams mixing. Delta H mixing is greater than 0, that is endothermic. That means absorption of heat takes place. And here delta H mixing is less than 0, that is exothermic. For ideal solutions, we took the example, or we can give the example of N-hexane, a mixture of N-hexane and N-heptane. Both are non-polar. Then you can give the example of benzene, toluene. For non-ideal solutions, for positive deviation, you can give the system alcohol water system, and here you can give acid water system. Now the relationship between, or the connection between Henry's law and Raoult's law. According to Raoult's law, for any volatile component, we have considered liquid solutions. So for any volatile component, it is Pa is equal to P naught A into XA. If you consider B, it is Pb is P equal to P naught B into XB. Now for Henry's law, for gaseous solute, if we take the relationship as Pa directly proportional to XA, or Pa is equal to Kh into XA. So, or you can also take Pb is equal to Kh into XB for these, making these B or same. So consider this as equation 1, this as equation 2. So when we compare equation 1 and equation 2, the constants are P naught A in equation 1, and here for Henry's law we have the constant Kh. The only difference between the Raoult's law applied to liquid components and Henry's law applied to gas in liquid, we can have, the only difference is here the constant is P naught A, that is the partial pressure of pure component A. Here it is Henry law constant, that is Kh. It is found that Henry's law is sometimes obeyed by liquid solutions. It is also observed that if the solute obeys Henry's law, solute obeys Henry's law, then solvent obeys Raoult's law. But it is found that the reverse is not true.